The autumn of 1942 was a grim season in the skies over Kent. Down on the tarmac of RAF Biggin Hill, a chill wind whipped across the airfield, carrying with it the scent of wet grass, high-octane fuel, and the ever-present tension of a war that was not going entirely to plan. It was the 3rd of November, just past 4 in the afternoon, and Sergeant Arthur Hobbs, a fitter and turner of 30 years from the railway works at Crewe, stood before a Supermarine Spitfire MKVB, serial number EP120. He stared at it not with the pride of a groundsman for his charge, but with the deep, abiding frustration of a master craftsman facing a puzzle he could not solve. The puzzle was, on the surface, deceptively simple. The aircraft, a beautiful, lethal machine of elegant curves and raw power, was stubbornly, inexplicably, slow. In the manuals, in the hallowed halls of the Ministry of Aircraft Production, the figures were written in stone. A Spitfire MKVB, powered by the glorious Rolls-Royce Merlin 45 engine, should be capable of 374 miles per hour at 13,000 feet. That was the speed promised by Supermarine's designers, the speed the Royal Air Force had paid for, the speed that every pilot depended on. Yet, EP-120, the personal mount of Flight Lieutenant Alistair Sandy McGregor, a fiery Scot with 2 kills to his name, could barely touch 350. In the unforgiving arithmetic of aerial combat, that 24-mile-per-hour deficit was not a statistic, it was a death sentence. 24 miles per hour was the gap between catching a homeward-bound Focke-Wulf 190 and watching its tail disappear into the clouds. It was the margin between having the energy to outturn your opponent and feeling the sickening thud of cannon shells ripping through your own fuselage. For the young men of No. 92 Squadron, it was the chasm between returning for a brew and a debrief, and becoming a fading voice on the radio before vanishing into the cold grey waters of the Channel. And Flight Lieutenant McGregor was not alone. Of the 18 Spitfire VS on the squadron's roster, a dozen were running sluggish. The pilots, a superstitious and pragmatic bunch, called them duds or plows. They reported it in their clipped, understated way after every sortie. The commanders documented it with growing alarm. The ground crews, the Irks, tore them apart and put them back together again, seeking the phantom ailment. They all reached the same maddening conclusion: it wasn't the engine. The Merlin 45s were paragons of reliability and power. Compression tests were flawless, the spark plugs clean, the fuel-air mixture perfectly calibrated by the SU. Carburetors. The superchargers whined at the correct pitch, delivering the precise boost required. Each engine was pushing out the 1,470 horsepower it was designed to. The power was there. The speed, infuriatingly, was not. Arthur Hobbs was not a university-educated aeronautical engineer. He held no degree in fluid dynamics. What he did possess were 15 years of shaping and wrestling with heavy metal in the smoke and steam of the Crewe locomotive works, and an intuitive, almost spiritual understanding of how mechanical forces flowed through stressed materials. His hands, calloused and stained with grease, could feel a vibration that no instrument could measure. The squadron's engineering officer, squadron leader Evans, a methodical Welshman who trusted data over instinct, had suggested the problem must lie in parasitic drag. Perhaps, he'd mused, the control surfaces were misaligned by a fraction of a degree. Perhaps there was microscopic damage to the stressed skin aluminium of the fuselage, tripping the airflow from laminar to turbulent. Perhaps the radiator intakes under the wings weren't drawing air cleanly. Hobbs, methodical in his own way, had pursued each of these theories with the tenacity of a terrier. He'd spent hours with feeler gauges and spirit levels, checking the alignment of ailerons, rudder, and elevators. He'd crawled over every inch of EP-120's skin, his fingertips searching for the slightest dent or ripple. He'd even fashioned an endoscope from a dentist's mirror and a torch to peer deep inside the intakes. He found minor imperfections, corrected them with patient skill, and sent McGregor up for another test flight. The result was a gain of one single, pathetic mile per hour. The deficit remained a chasm. So, while the engineers pored over airflow diagrams, Hobbs began to look where no one else was looking. He looked at the propeller. The Spitfire VB was fitted with a Rotor constant-speed propeller, a 3-bladed marvel of engineering. Each blade, forged from a high-strength aluminium alloy known as hydrolignum, was a complex aerofoil, designed to bite into the air and convert the Merlin's ferocious rotational power into forward thrust. But propellers are not just spinning paddles, they are rotating wings. And like any wing, their efficiency is utterly dependent on their angle of attack, the angle between the blade's chord and the onrushing air. If the angle, or pitch, is too fine, the blade slices through the air with little resistance but generates no real pull. If it's too coarse, the blade stalls, churning the air into a vortex of useless turbulence instead of clean thrust. The rotor system was a masterpiece, automatically adjusting the blade pitch to be coarse for a powerful takeoff climb and finer for high-speed cruise. The mechanism was hydraulic, precise, and, according to every test, working exactly as designed. But Hobbs noticed something buried deep in the rotor specifications, a detail the engineers had accepted as a design limitation. The blade profile and its pitch range had been optimized for the Spitfire's designed maximum speed of 374 miles per hour at 3,000 engine revolutions per minute. Those were the parameters. But what if the aircraft was capable of more? What if the true bottleneck wasn't the airframe or the engine, but the very propeller that was supposed to drive it forward? It was a preposterous idea, a suggestion that the designers at Rotor and Supermarine had missed something fundamental. And if you want to know how this absurd notion, born in the mind of a railway fitter, would go on to change the performance of Britain's most iconic fighter, please, click that like button and subscribe for more stories from the hidden corners of history. Hobbs sat in the noisy canteen with a mug of strong, stewed tea, a pencil, and the back of a maintenance chit. At 374 miles per hour and 3,000 revolutions per minute, he calculated that the tip of each propeller blade was scything through the air at nearly 980 feet per second. The speed of sound at sea level is around 1,125 feet per second, but the Spitfires weren't fighting on the deck. Their battles were fought at 20 or 25,000 feet, where the thin, cold air lowered the speed of sound to about 1,000 feet per second. At that altitude, the blade tips were already entering the transonic realm. They were creating their own miniature shockwaves, invisible barriers of compressed air that generated immense drag, effectively putting a brake on the entire aircraft. Hobbs's theory was radical. If he could somehow reduce the pitch of the blade tips by just 2 or 3 degrees, making them finer, they would slice through the air more cleanly at high speed. The reduction in tip drag might be enough to unleash the Merlin's full potential and allow the aircraft to accelerate past its current, artificial limit. The theory was elegant. The practical reality was a nightmare. The rotor propeller blades were made of duralumin, an aluminium alloy heat-treated and hardened to withstand incredible forces. They were designed to be utterly rigid. You couldn't just bend them. Any attempt to reshape them using cold force would result in microfractures, weakening the blade to the point of catastrophic failure. At 3,000 revolutions per minute, each blade was subjected to centrifugal forces measured in the tens of tons. A structural weakness wouldn't just cause a vibration, it would cause the blade to shear off at the root, disintegrating the propeller hub, tearing the engine from its mountings, and, in all likelihood, killing the pilot in a split second of explosive violence. Hobbs took his idea, sketched out on the greasy chit, to squadron leader Evans. The Welshman listened patiently, his brow furrowed in concentration, before giving the exact response Hobbs had anticipated. "Sergeant," Evans said, his voice quiet but firm, "are you seriously suggesting that we physically alter a certified, life-critical component manufactured to the highest possible tolerances?" He took off his spectacles and polished them. "First, we don't have the equipment to reshape hardened duralumin without destroying its temper. Second, if we modify a blade and it fails in flight, we will have murdered one of our own pilots. Third, this would invalidate every airworthiness certificate we hold. The answer, I'm afraid, is an unequivocal no." Hobbs didn't argue. He had expected as much. He simply looked the squadron leader in the eye and asked, "Sir, would you object if I proved the theory on a single, damaged blade? One that's already been written off and is due to be sent for scrap?" Squadron leader Evans stared at Hobbs for what felt like a lifetime. He saw not insubordination, but a deep, burning conviction. He thought of the 3 pilots his squadron had lost in the past month, all of them last seen in a desperate dive, trying to escape the claws of an FW-190. Finally, he gave a slow, deliberate nod. "One blade, Hobbs. In the workshop only. It is never to be fitted to an aircraft. And I want an engineer to witness and document every single step you take. Is that understood?" On the 5th of November, in a quiet corner of the main hangar, Hobbs was given his test subject, a rotor propeller blade, part number RA654, which had been removed from a Spitfire after a bird strike left a deep gouge near its root. The blade was scrap. Hobbs laid it gently on a set of trestles and began his examination. It was a beautiful object, a perfect blend of form and function. He measured its pitch, 45 degrees at the root, tapering to a fine 24 degrees at the tip. His goal was to twist that tip section, the final 2 feet of the blade, by exactly 3 degrees, from 24 down to 21. To do that with hardened duralumin, he would need to apply the ancient blacksmith's art of heat and pressure. He knew from his days in the loco works that every metal alloy has a critical temperature window. Below it, the metal is too brittle. Above it, it loses its structural integrity forever. For this particular alloy, that window was perilously narrow. Between 490 and 510 degrees Celsius, there was a brief period where the metal became malleable without being permanently compromised. Hobbs would have to heat the blade tip to precisely 500 degrees Celsius, hold it there while he applied the twisting force, and then cool it in a highly controlled manner to prevent thermal shock from creating invisible, fatal cracks. The station had no computer-controlled heat treatment ovens, no laser pyrometers. But Hobbs had an oxyacetylene torch, an infrared thermometer borrowed from the engine shop, and 15 years of experience reading the temper of hot metal by its color and shimmer alone. He built a heavy steel jig to hold the blade root immobile. With a piece of chalk, he marked the section he intended to heat. Then, he lit the torch. Its flame burned at over 3,000 degrees Celsius, a tool of immense power and subtlety. Hobbs didn't point it directly at the blade. Instead, he played the flame across the surface in slow, deliberate, overlapping circles, letting the heat soak into the aluminium gradually, evenly. Every 30 seconds, he would pause and take a reading with the thermometer, his movements calm and economical. The temperature climbed. 450 degrees. Still too cool. 475. Getting close. 495, 502 degrees. He was in the window. Putting down the torch, Hobbs picked up a huge, custom-made spanner with a 5-foot lever arm. He fitted it over the blade tip and applied slow, steady rotational pressure. The duralumin, which minutes before had been as unyielding as steel, began to give way, twisting like warm toffee. It moaned in protest, a low groan that echoed in the cavernous hangar. Hobbs watched the angle gauge he'd fixed to the jig, his muscles straining. 1 degree. 2. 2.8. 3. He stopped, holding the pressure for a full minute to allow the metal's crystalline structure to settle into its new shape. Then came the cooling. He couldn't just quench it in water, the shock would shatter it. Instead, he used a low-pressure compressed air line, bathing the hot metal in a gentle, cooling breeze. It had to be gradual, slow, allowing the stresses to dissipate naturally. Over 10 minutes, he brought the temperature down below 200 degrees, then left it to cool to the ambient temperature of the hangar. An hour later, it was cold to the touch. Hobbs ran his hands over it, then inspected it under a bright, angled lamp, searching for the faintest hairline crack. He saw nothing. He performed a dye-penetrant test, painting the twisted section with a thin red fluid, wiping it clean, then applying a white developer. If there were any surface cracks, the red dye trapped within them would bleed into the white, revealing the flaw. The developer remained pristine white. No cracks were visible. He measured the new pitch angle at the tip. It was 20.8 degrees. His target had been 21. A deviation of 0.2 degrees. It was more than acceptable, it was miraculous. But the crucial question remained. Had he weakened the blade? Squadron leader Evans ordered a structural load test. The single, modified blade was mounted in a test rig in a reinforced bunker, a powerful electric motor designed to spin it to simulate the forces of flight. They ran it up, past the Merlin's 3,000 revolutions per minute red line, to the equivalent of 3,500 revolutions per minute. The blade held firm. No flutter, no abnormal vibration, no failure. Hobbs had reshaped the impossible without breaking it. Type Spitfire in the comments if you're enjoying this incredible true story of British ingenuity. Squadron leader Evans, a man converted, authorized the next, far more dangerous phase: modify a full set of 3 blades and install them on an operational Spitfire for a test flight. On the 10th of November, Hobbs and a small, trusted team of Irks worked through the night. They took a propeller assembly scheduled for routine replacement and applied the exact same painstaking process to each of its 3 blades. Heat to 500 degrees, twist by 3 degrees, cool slowly, inspect, test. It took 14 hours of intense, unbroken concentration. By dawn, they had a complete, modified rotor propeller, its blades now pitched at 21 degrees at the tips. At 7:30 a.m. on the 11th of November, 1942, the modified propeller was fitted to Spitfire EP-120, Flight Lieutenant McGregor's sluggish aircraft. The pilot himself was told only that his prop had been replaced with a freshly balanced one from stores. The test plan was simple: climb to 20,000 feet, level off, and then push the throttle to full combat power. At 9:41 a.m., McGregor lifted off from Biggin Hill's grass runway, the familiar roar of the Merlin a comforting sound. The sky was a brilliant, cloudless blue. He climbed steadily over the patchwork fields of Kent, the white cliffs of Dover a gleaming line in the distance. At precisely 10:05 a.m., he leveled out at 20,000 feet and radioed to the control tower that he was commencing the speed run. He pushed the throttle lever smoothly forward to the gate, the engine revs climbing to 3,000. The Spitfire surged forward. 320 miles per hour, 340. The needle swept past 350, the point where the aircraft would normally start to labor, the acceleration tailing off. But it didn't tail off. It kept climbing. 360, 370. McGregor's eyes widened. He was already past the official top speed, and the Spitfire felt alive, hungry for more. 380,390,400 miles per hour. He keyed the radio, his voice a mixture of disbelief and exhilaration. Biggin Tower, this is Blue Leader. Are you quite sure my airspeed indicator is calibrated correctly? I'm reading 405 miles per hour and still climbing. The tower confirmed the instrument had been calibrated just the day before. McGregor pushed on. 410, 415. At 10:11 a.m., Spitfire EP-120 topped out at a staggering 418 miles per hour. 44 miles per hour faster than its certified maximum, and nearly 70 miles per hour faster than it had been flying just the day before. He held the speed for 5 minutes, checking his instruments. The engine temperature was stable, oil pressure was normal, and the controls felt crisp and responsive. The aircraft was performing flawlessly. When McGregor landed and was finally told the truth that his propeller had been bent in a workshop with an oxyacetylene torch, his response was pure, unfiltered pilot. "I don't care if you heated the blades with a bloody dragon," he said, grinning from ear to ear. "I want this done to every Spitfire in the squadron." Yesterday, squadron leader Evans sanctioned a limited operational trial. Over the next 2 weeks, Hobbs and his team modified the propellers on 6 more aircraft from No. 92 Squadron. The results were consistent, an average speed gain of 42 miles per hour. The modified aircraft saw their first real test on the 28th of November, during a fighter sweep over occupied France. McGregor was leading a section of 4 modified Spitfires when they spotted a flight of 8 Focke-Wulf FW-190s harassing a formation of Boston bombers. The FW-190A, with a top speed of around 408 miles per hour at that altitude, was the scourge of fighter command. It could normally outperform the Spitfire V in speed and rate of roll, allowing its pilots to dictate the terms of engagement. But not today. As the German pilots saw the Spitfires diving to attack, they did what they always did, pushed their throttles forward and prepared to pull away into a shallow dive, confident in their superior speed. It was a fatal miscalculation. McGregor's Spitfire didn't just keep pace, it closed the distance with terrifying velocity. The dogfight lasted less than 6 minutes. The result was a massacre. 4 FW-190s were shot down. The rest scattered, their pilots utterly bewildered by the impossible performance of the supposedly inferior Spitfires. Not a single British aircraft was lost. McGregor's combat report was emphatic. The 190s could not get away from us. They could not outclimb us. They could not outrun us. The propeller modification has completely altered the tactical situation. Recommend immediate implementation across all Spitfire wings. But the Ministry of Aircraft Production at Farnborough had a different view. Their engineers argued that Hobbs's modification, while demonstrably effective, was an uncertified, unscientific hack. There was no long-term metal fatigue data, no harmonic vibration analysis, no standardized protocol to ensure consistent quality. Their official recommendation, issued in mid-December, was to reject the field modification until Rotork could conduct a full study and develop a certified manufacturing process. The estimated time for official certification, 12 to 18 months. Air Vice Marshal Trafford Leigh-Mallory, the famously pugnacious commander of No. 11 Group, read the report from Farnborough. He responded with a terse memorandum that became an instant, if unofficial, legend within fighter command. Farnborough can take 18 months to certify what my fitters have already proven in combat. In the meantime, we will continue to kill Germans with propellers modified by sergeants. If the ministry has any objections, they may present them in person to the bomber crews whose lives these Spitfires are saving. Between late 1942 and the summer of 1943, over 200 Spitfire VS operating from Kent and Sussex had their propellers unofficially modified using variations of the Hobbs twist. It was never an official policy. It was simply something that worked. Rotork eventually did certify a new blade profile incorporating the change in late 1943, after spending over a year and a considerable sum of money to scientifically validate what Arthur Hobbs had discovered empirically with a torch and a thermometer. Sergeant Hobbs never received a medal for his innovation. He was never promoted specifically for this contribution. His name appears in no official technical manuals. But among the pilots of No. 11 Group, the quiet fitter from Crewe became a legend. While the engineers in their clean labs were calculating, and the bureaucrats were debating certifications, Art Hobbs was giving British pilots an extra 40 miles per hour of lethal advantage over the best fighters the Luftwaffe could produce. And in the skies over the English Channel, 40 miles per hour was the difference between being the hunter and the hunted. After the war, Arthur Hobbs returned to Crewe. He went back to the railway works, eventually becoming a foreman in the fabrication shop, a position he held for 32 years. He retired in 1980 and passed away peacefully in 1991. His obituary in the local paper noted his wartime service with the RAF but made no mention of the twisted propeller blades that gave the Spitfire its vital edge during one of the most critical phases of the air war. His legacy, however, endured. In 1946, the RAF established the Rapid Field Modification Program, a new department specifically designed to fast-track the evaluation and adoption of technical innovations developed by ground crews under combat conditions. The program's founding charter explicitly cited the unauthorized propeller modifications of 1942 as the prime example of valuable technical innovation that had been delayed by an overly rigid certification process. What do you make of this extraordinary story? Did you know the crucial role an unheralded railway fitter played in mastering the Focke-Wulf scourge? Let me know your thoughts in the comments, and be sure to subscribe to our channel. We bring you verified, fascinating stories that have shaped history from the ground up, every single week. Activate the notification bell so you never miss an episode. Because sometimes, the greatest innovations don't come from engineers with doctorates, but from a sergeant with a blowtorch who simply refuses to accept that something cannot be done. That is the lesson Art Hobbs taught the RAF from a drafty hangar in Kent, a lesson the pilots who flew at